Again, welcome back to Precalculus. These lectures cover the functions. Our main objective is to learn how to use function notation, also how to state the domains and ranges of certain functions. We're also going to learn how to perform operations with functions and how to find the composite of two functions. Here we can use function notation to indicate that y is a function of x. So the function is denoted by f, and we can write it as y equal to f at x. Now, for a specific value of x, for example, f at 2 means when s equal to 2, what is the value of the function f at x or y? Example 1, electronic income tax returns. Here we say the number of personal income tax returns filed electronically, T, in millions, can be modeled by the function T at x equal to 6.35x plus 4.65. Now, x is the number of years after 1995. Now, here they say we should find T at 20. So, which means at 20 years. Then after that, we'll write the sentences that explain the meaning of the results in part A. So let's start with the part A. Now we know x equal to 20 because it's 20 years. So we substitute x with 20, and this gives us the value to be 131.65. So 131.65 means that in 1995 plus 20 years, which is into 2015, approximately 131.65 million personal income tax returns were filed electronically. Now, when we look at the question, we say T represents in millions. T is the number of personal income tax return filed electronically in millions. So from the source, this source came from Internal Revenue Service. We started from 1995. So 1995 means 0, x equal to 0. And 20 means 2015. So that will be the result. Now let's look at second example. Here we are going to find the domain of each of the following function. So we have y equal to 4x squared. Now to find the domain, here we said y equal to 4x squared. It doesn't matter. Any value of x will give us a value of y. So this means it will be negative infinity to positive infinity. There's no restriction of the value of x. So here we say there are no restriction on the number substitute for x. So the domain consists of all real numbers because the square of any real number is non-negative. So 4x squared must be non-negative. Now, second value, we can see that we have a square root. So we know we don't want the square root of a negative value. In a complex number, square root of a negative value can be fine. But in real numbers, a square root of negative value, there's no solution. So this means B, we know that there's a restriction that 4 minus s cannot be a negative. So when we look at here, we don't want x value to be more than 5. So here does the domain consists of only numbers less than or equal to 4. So here our domain, again, the question said we should find the domain of each of the following function. The domain will be the possible s value that can give us a result for y. So if I have a square root of negative value, I can get a y value. So here again, the domain will be values that is equal or less than 4. Second equation, we want to make sure that we don't divide the value by 0. Because when we divide the value by 0 or we find a negative value of a square root, there's no solution. So those values cannot be a domain. So that is the C, y equal to 1 plus 1 over s minus 2. It's undefined at s equal to 2 because 1 over 0 is undefined. So this means the domain can be any value except positive 2. So we say the break when s equal to 2 indicate that s equal to 2 is not part of the domain. So it can be any value except 2. Now let's go through the operations with functions. Now with functions, we can perform almost every arithmetic operation. So for example, the sum, difference, multiplication, division. So if I want to find the sum of two functions, all we need to do is to add them. So we add the like terms together. Difference also the same thing. Multiplication will multiply the functions. Division will divide. So let's see an example. Also before that, let's look at the composite function. So here, if we say G composite F at X, it means that the argument, which means here, we have going to give F at X to G. And if F composite G means G will be the argument, so G at S will be inside F. The best way, again, is to do some examples. So our example here is F at S equal to 2s cubed plus 1, and G at S equal to S squared. Now, they say we should find the composite of G and F at X. So this means G composite F at X means F at S will be inside G, which means anywhere I will see, if I look at the G, for example, G here is S squared. Anywhere I see S squared, I'm going to substitute with F at S function. So here we are going to say G 2s cubed plus 1, because we have only one x squared. So this means G 2s cubed plus 1 all squared. And that's what we have here, 2s cubed plus 1 all squared, because G at S is S squared. So the way we see S, we substitute with F at S, which is 2s cubed plus 1 and S squared. Then from here, we can solve the problem. Now with B, we have F composite G. So first F will be outside. Anywhere we see X at F at S function, we substitute with G at S. G at S is S squared. So we have F at S squared. And then we have 2s cubed. We substitute S with S squared. So we get S squared cubed. And that gives us 2x to the power 6, because 2 times 3 is 6. So that will be the conclusion of these short lectures. The main goal here again is to go through how we can find the domain of a function, how we perform function operations, multiplication, division, addition, and subtraction. Then we also saw the composite functions. So again, see you in the next lectures, and thank you for your time.